What pushes a car physically down the road? Because you have to have an unbalanced force acting on the car to make it accelerate forward, correct? And that force is equal to the mass times the acceleration. But what physically is pushing the car down the road? The friction between the tires and the road. So what object is acting on the car to make it go down the road? The road must be pushing the car down the road. Is that right? So here we've got a road and we've got a car, and let's turn it on. Okay? And let's make it go forward. I think this is funny. Well, it had a road and it had a motor and it had all this stuff, right? Okay, here, we'll turn off the motor. There you go. Okay. But of course, the road in this case had much less mass than the car, right? So this is equal action, opposite reaction, right? Normally when the road pushes the car back, when the car pushes the road backwards, the road pushes the car forward. And normally the road has a lot more mass because it's attached to the earth, for example. Okay, but in this case the road was actually quite lightweight. But if you look, the car actually does move forward a little bit. Watch. Just a little. But watch just the car now. It's like, oh, you see that? Okay, it actually does move forward a little bit, but since it's got so much more mass than this is the thing that shoots backwards. Or is it Mr. Hamilton that does that, where you stand on a skateboard, and if you can jump across a line, he gives you like extra points or something like that, right? Is that what it is? Yeah. And of course, you know, the skateboard has so little mass that you try to jump and the skateboard goes flying and you just go a little bit, right? So the real trick there would be to bring a skateboard in that weighs as much as you, and then you'll each have equal velocities, right? You won't go as fast as if you jumped from the floor, but you will go faster than if you jumped from a 2-pound skateboard or something like that. Little applause for the car. That's right. Oh, the horn. Well, there we go.
Another trick to get in the jumping over the line. Sort of just lie down on the skateboard and get to swim a bit. This is like a line jump.
You swim, yeah, swim. Okay, so the next thing we got to do is we've got to look at this, because this is going to be the crux. This is the crux of the entire chapter. Okay, is this this F equals ma. Okay, so here's the deal, right? Is that this that this is force, and force is in newtons. Okay, mass is in kilograms. Okay, and then acceleration is, of course, in our meters per second squared. Right, so F equals ma. And in general, for acceleration, I might give you a Suvat problem. So just when you thought it was safe to do physics again, we're going to go and we need you to be able to solve these problems so that if a object is stopped from a certain speed in a certain distance, you'll be able to figure out the acceleration for that, right? For mass, the only tricky thing for mass is that if they give you grams, right? Well, 1,000 grams is 1 kilogram, right? So you don't want to use grams, you want to use kilograms, and 1 kilogram is, I had a kilogram, I passed it around, I wonder where it went. Does anybody see a mass sitting on a counter? There it is, all right, it made it all the way back, that's good. Okay, it's good that everybody this is 1 kilogram, it's not le grand K, okay? Le grand K is the big kilo. It is the kilogram that defines all kilograms. Okay, it is a bar of platinum in France, and I tried to get the actual kilogram for this lesson, and they said something in French. It was very sarcastic. Okay, and so we have this one, and this one is based on that kilogram, and it's probably plus or minus 5%. Now, if I hold this in my hand like this, I can feel the weight of it. That would be the force of gravity acting on this kilogram. Okay, if I take it like this and I go, I can feel its inertia. Now, if I went into outer space, it would not have any weight. I could put it here and it would just sit there. Yeah? Be like, where did I put that kilogram? Here it is. Yeah, right? And if I put my hand under it, it wouldn't press on my hand. I wouldn't feel any weight. But if I grabbed that same kilogram and went like this, it would feel pretty much the same way. I would feel a resistance to going back and forth because that's not the nature of objects. It wants to keep going in the direction it's going. Yeah? Okay? I'll pass this around. This is a kilogram, but it's not the kilogram. Yeah? Difference between the indefinite and definite article. Okay? And then the final thing that we have to sort of double click on here and understand is that this is the net force. Okay? By net force, we mean the part of it that's not canceled out. Okay? So if we've got like two forces acting on some object, if I've got 5 newtons this way and 2 newtons this way, the net force would be 3 newtons to the right. Yeah? That's when we say net force, that's what we mean, is the part that's not balanced out. Or worst case scenario, right? We could possibly have a problem where there's these 3 forces acting on an object. What would we do with that? Would we add them as vectors?
Yes.
Yes, we would. We would go, there you go, right? We would add them as vectors and come up with one force, right? And then that would be what we'd use. So really it means the net force, when we get right down to it, it's the vector sum of all forces. And this is, we're going to spend quite a bit of time doing stuff like this. We're not really going to do too many like forces at different angles, but I think there's like one example in the textbook that we'll do of that. But ultimately that's what it is, right? So all of these things we're going to have to figure out. The forces are vectors. Acceleration is also a vector. It's also in some direction. So we've got to be very careful about that. It's either plus or negative, minus or something like that, right? Okay. So let's do a couple examples here. Let's do some object goes from 0 to 12 meters per second in 3 seconds, right? And it's a 5 kilogram object. Let's say it's 5.0 kilograms. Yeah? And so the question is, what's the force, the net force acting on it? What do I have to do with the Suvat stuff first?
Well, you have to
find the acceleration, right? Now we just care about acceleration. Okay? So I'm going to find the acceleration. I'm going to use V as U plus AT. The formula you may have forgotten on the test. Okay? The final is 12, the initial is 0, plus A times 3. And then A is equal to 4 meters per second squared. Right, so that's step 1 is, okay, we had some cute problem to do. Now we've got the acceleration. We know the mass. Now we can find the force. Right, so the next step is F equals ma. So F equals 5 kilograms times 4.0, right? And that ends up being 20 kilogram meters per second squared, right? Or 20 newtons. And it's capitalized. It's newtons. It's newtons. It's like Sir Isaac Newton. So you've got to capitalize it because it's his name. You can get in trouble not capitalizing that name. So this is about as hard as a problem is that we would ever get in this first part, right? And then eventually we're going to make things harder because one of the forces, there's going to be more than one force acting on it. One of them might be the weight of the object, the force of gravity, right? Then we'll tip the plane. We'll tip it up like this, and now part of the weight is acting down the plane, right? And we've got to incorporate that, and then there could be a friction force, and we could apply some force, right? So this is ultimately it's going to be force 1 plus force 2 plus force 3, right? Ultimately, yeah. Ooh, what was that? Bam! It's a loud kilogram, She dropped it out loud. Okay, so try this one. Put that on a whiteboard. Show me the answer.